In our little lesson lecture today, we're going to be deriving centripetal acceleration and centripetal force. And I could tell you the equations, but I want you to have the experience of trying to follow through with what is the thinking that had to be done to obtain these equations. And we know right now, kind of from past units, that Newton's second law tells us that the net force is equal to the mass times the acceleration. So what is the centripetal force equation, though? And what's the centripetal acceleration equation? It's not as simple as just what we see here. And so what I have drawn so far, what I'd like you to have, is that we'll have a ball moving counterclockwise. So it'll be moving that way, and then that way, and this way, and this way. So it's going counterclockwise in a circle of radius r, and it's moving at a constant speed. And I have a dot here with the center of my circle and my origin right here. And what I'd like to do is actually go along and draw really just our radius and label that r. So we really just have the radius here, nice and easy, and we can call that r. But if the ball has that radius at the first position, it has the same radius at the second position. The string isn't changing, or whatever it is that this is causing this ball to rotate isn't changing. So we have the radius, and let's call where it starts A, and let's call this later position B. All right, fantastic, easy enough. And in the time it takes to go from A to B, it's gone through some angle that we will call theta. Nice, fantastic. So what I'd like to do then is actually trace along this little segment of the circle that our ball has gone along. And I'm going to use blue for it, blue right here. So this is our arc. It's the segment of a circle, so it's this arc. And let's just call it arc AB. Now, the neat thing here is we said that the ball is moving counterclockwise in a circle, radius r, at a constant speed v. So the speed is not changing. And so if that's the case, then, well, if the distance is this arc, right? The distance is the arc. Well, we can just take a little note on the side here. You don't need to write this. But if we know that velocity is the change in distance over the change in time, but our distance is the arc here, we could rewrite this so that we have velocity times the change in time is the change in distance. And so in our case, our distance here is this arc really of itself. And so we'll say that this arc is equal to the size of the velocity, because the velocity has a direction part too. The size of the velocity multiplied by how long it took. So really this is just saying distance is equal to velocity times time. That's how far the ball has been displaced and however long it took to get there. Now, making this a little kind of more interesting, we're going to add in the velocity for the ball as well. And so at the right here, when we're kind of looking here, well, the ball would be going up. And so but the velocity is speed with direction. So the velocity is some length going up. And then over at this position B, the velocity is the same length, but it's in this new direction. So the speed we said isn't changing, but the velocity will be because it has this changing direction. So I've actually already gone ahead and drawn my velocities here, and we can see that they are about the same size. And I'd like to mention here that it should be tangent to the circle. And now maybe you're going, what does tangent mean? Tangent means that it just barely touches the circle. And so I've gone and called this velocity 1 and velocity 2, keeping in mind that the size of both, the length is the same because they're the same speed here, really. Okay, fantastic. Now, we'll do one more thing, and the one other thing is I actually want to connect A and B by a straight line. So we won't have this little slice of a pizza anymore, or a pie, or whatever have you. And we'll use blue again for this. It's going to be really this triangle now. We have this triangle. And so imagine that I can kind of duplicate the ball. And so it's at point A, and then there's another ball at point B. We could connect those by this little blue straight piece of string, and this will be chord. So it's like this little taut chord A, B. And it's also worth mentioning that we have an isosceles triangle here. That means that two side lengths are the same. They both are radius r. And that means that the angles that kind of match are the same as well. So we have these little angles. We can call them alpha. Just it's a little fish kind of right there, little Greek symbol. And so, great, we have a whole bunch of work for this first triangle. Now, what does it matter? What are we doing with this? Well, what I would like to do actually now is I would like to take those two velocities again, and I would like to go and put them down here, and we're gonna actually kind of draw them or put them actually centered over here, kind of at the center of our circle, or we could put them over here on the right, whatever really seems more convenient for you. If you made your circle really big, you probably want to put it inside the circle over here. If you don't want to put it inside the circle, you like having the space over on the side, that works fine too. It doesn't really matter, but we're going to actually line them up, and we're going to line them up going from the origin. And this has to do with vectors, actually. This kind of has to do some vector addition. And what I want to go ahead and draw is I want to draw a line connecting them, and then I'll tell you what it is, and we'll get kind of why that's so. So looking actually kind of back to just the ball itself as it goes from point A to point B. The velocity was going up with some size, and now it's going at some funny angle, but it's the same size. So there's been a change in the velocity. And so if we go from this first velocity to this second velocity, there's been some change in velocity. And so thinking of vector addition here, and you don't need to write this next part, you could say that the first velocity plus the change in velocity gives you the second velocity. That's absolutely correct as far as vector addition. We've taken the tip of the first one and we've stuck it where the tail of the second one is, and that works. You could also have thought of it in terms of the first velocity minus the second velocity gives us the change in velocity. It's like, well, if you subtract them, that's giving you the difference in velocity. And so we can leave this here. It won't be in the way or kind of bothering us. What I want to do now is call this point C and D. So we really have these two triangles, okay? And what I want to mention with these two triangles is that if the angle to go from A to B was this angle theta here, but we've gone from velocity 1 to velocity 2, well, we've gone through the same angle because they're starting at A and at B. And so we actually have the same exact angle theta here, which is pretty sweet, pretty convenient, really nice for us here. So with that in mind, we actually can use a little geometry. And the geometry that I would like to use is actually a theorem from one of your past classes. Now, if you're not a huge fan of geometry, it's okay. It'll be pretty minimal. We'll do a little geometry, a little algebra. We'll even sneak in a little calculus under the hood, but hopefully sneakily enough that you're not really aware that it is calculus here. But what I want to say is that we have these two triangles. We have this triangle A to O to B and back, and we have this triangle C to O to D. And I'm saying them in that order so that they both have O in the middle of them. What I want to say is that this first triangle, AOB, is similar to, and similar means that the side lengths are proportional and that the angles are all the same. The corresponding kind of the matching angles are the same to COD, that triangle there. Now, this little wiggly line, as I just said, that means similar. Now, here's the proof for it, because I don't want you just to take me on face value here. There's this theorem, and the theorem is, so we can say it's due to the SAS theorem. What's SAS here today? No, it's the side angle side theorem. That's what that actually means, SAS theorem. So we can write side angle side. And what that really tells us is that the ratio of one set of sides. So let's say we took the side that is to the right of the angle. So that would be V1 here and R here. If we took the ratio of those, well, that ratio would just give us, well, V1 over R. And since we're caring about side length, I can just take the magnitude here. And then the side angle side theorem has to go in order. So we have this ratio of sides, and then we have an angle that's the exact same. Well, we already know that they do have the same angle here. So they have the same angle. And then that the ratio of the other set of sides is the same as the ratio of the first set of sides. So really that's saying then that this V2 over R here again. But we know that since the ball's going at a constant speed, we know that really the size of these velocities are the same. So what we can write then is that this size of V1 over R is equal to the size of V2 over R, okay? And we know that both have an angle, get rid of these, have an angle of theta between them. So that's really the majority of our trigonometry here for us. Now, what this means, though, just kind of taking a visual note here to remind you, is similar triangles have equal matching sides. So equal matching, ooh, I can spell today, matching sides and proportional side lengths. So the side lengths are not the same, but they're proportional to each other. Now, furthermore, they actually are isosceles triangles as well. So both are isosceles. And that means that they have two sides the same length. And so what that tells me then is that they have the same exact angles. So we can actually go and fill in that this angle and this angle are also alpha. It's essentially these two triangles are the same. It's just they're rotated and kind of like scaled up or scaled down. They are the same triangle in essence. That's what this really is telling us. So with that being the case, then we can absolutely, in all correctness, write that the angle, oops, where's my black? The angle, that's what that little sandwich nose kind of looks like there. Whoa, I'm not sure what happened there, sorry. That this angle of OAB, so that means OAB, that means this angle, the one that's kind of in the middle, is equal to the angle of OBA. But that's also, because the triangles are the same, they're just scaled up or scaled down, that's also equal to the angle going from O to C to D, this angle here in the middle. So we see our OCD. Some of you that maybe have a little OCD, sorry there. And that's also equal to this angle, which we would call ODC. Angle ODC. So we have these equal angles. Okay, fantastic. Now, what that means, though, is that we have the ratio of the sides of similar triangles are equal. So what I can do is I want to focus on this chord and my delta v here, my change in velocity. So what we can do is actually we can write here that the ratio of the sides of similar triangles are equal. So the ratio of sides of similar triangles are equal. So really all that means is if I took this side and divided them, I'd get the same ratio as this side and this side divided. The matching sides have the same ratios. And so what we can do is exactly that. And I want to start with my chord here, not the little curvy part, but the straight one right here. So we'll write out that we have this chord AB, and I want to divide that by the radius of my circle. Well, if I'm taking the chord here and I'm dividing by the radius, the matching thing to do with this smaller triangle would be to do delta V divided by V1. Delta V, the change in velocity divided by V1. But since we're caring about just the size, not the direction, it's side lengths, I don't need to put a 1 here or a vector. I'm just going to leave that as V, which is now the speed itself, okay? And we're going to come back to this. I want to circle this, label this like our equation 1. We're going to actually do a little finagling and get this in a handy version that's going to give us our final result here. Now, what I want to look at is this big triangle. And I want to look at it in the case where this side length right here actually starts collapsing down. So it's actually coming closer and closer down here, like the cover of a book closing. As it comes farther and farther down, and we can even just sketch one in to see here, as it were to come closer and closer down, and it would probably be around here really, we can see actually that the two different parts in blue, that are right here, we have this little segment of my arc AB and this little segment of my chord AB. Those look really close in length. They're actually almost the same already. And so the idea is that the farther this section falls downwards, the closer and closer chord AB and arc AB get to being the same value. And so the way that we could write that is that as this angle gets closer and closer to 0, well, these two become the same value. And that's what we'll write. So we'll put down here that in the limit, this is kind of a fancy way to write it, in the limit that our angle approaches 0, that's a pretty fancy way to write things, in the limit that it approaches 0, well, our chord AB becomes arc AB. So really I'm saying that in this limit that our angle goes to 0, these two are the same thing, and we can substitute them for each other, okay? Now, the reason we're saying this and we're looking at this really is that if we're looking at the ball itself going along that circle, we want to find the velocity at any instant, not an average. We want to find that instant. And so what we could say then is that the instantaneous velocity, so the instantaneous velocity would be found to be, or is the change it's traveling along that arc. It's traveling along the circle itself. So it's the change in arc AB. And if we want to find velocity, well, it's just distance, so the distance along the arc divided by our time here. And that's really just displacement divided by time would give us the velocity itself. So let's write that out kind of a little more formally here. We'd say then that, well, we know velocity is the change in displacement over the change in time, but since it's traveling along, well, this arc right here, we can say that that's really going to be our arc AB, however far along that we end up letting it go over our change in time. Now, if I wanted to go ahead and get this arc alone, though, I want to find just that distance alone. Well, it's just like getting x alone here. I'd multiply time over to both sides, and we'd have that our velocity multiplied by time is equal to our arc AB. But we just said that the arc and the chord are replaceable. We can swap them out with each other. So I want to go ahead and just cross this guy out, and we'll just put our chord AB here. So now what I would like to do is let's plug this in. Let's plug this into that equation 1 that I set up here. So we now have something that's equal to chord AB that we can plug in for chord AB right here. That's what we'll do. So looking at that then, plugging in V delta T for the chord right here, that's what we're going to do. We're just going to rewrite then that velocity times the change in time divided by the radius. And let me slide this over. So this number 1 becomes this velocity times time divided by our radius equal to the change in velocity over the velocity itself. Now, we're going to do one little swap here, one little bit of algebra gymnastics. I want to multiply v to the left side and divide by time on the right side. And so if I do that, so divide by delta t and multiply by v on both sides. Well, if we were to multiply v on both sides, well, the v, we'd have a v, and we're dividing by t here, and then a v dividing by t here. Well, we end up having that the t's would cancel here, and the v's would cancel here. So we can just rewrite this then as v squared over r is equal to delta v over delta, that was a terrible, delta t. Now, we actually have done something pretty incredible here, because if you recall, the change in velocity over the change in time, that's just acceleration. That's all this is. So in the case of something moving along in a circle, like this ball going from A to B, what we end up having is that the velocity squared divided by the radius is the centripetal acceleration. And so maybe you're wondering already, going, I thought the ball wasn't speeding up or slowing down though. So how can it be accelerating? Well, it's changing direction. And if the direction is changing, well, the velocity is changing. And that is by definition an acceleration. And so maybe you're wondering, what direction is that acceleration in then? Because if we think here and you go, well, if the ball were to accelerate forward, it would go faster. If the ball were to have an acceleration backwards, it would go slower. And so what we need is an acceleration pointed in a direction that makes the ball not speed up and not slow down and stay in this circle that we've been looking at. And the only option for that would be an acceleration that's pointing towards the center of our circle. That means that actually the force is going towards the center of the circle, because net force is equal to m times a. So an acceleration pointing towards the center of our circle would be due to a force pointing towards the center of our circle, which is pretty incredible. So this means that this is also our centripetal force is going towards the center. So with our centripetal acceleration value, we can rewrite Newton's second law to find now the centripetal force. Well, that's just mass times the centripetal acceleration. So we can plug in and see that it's mass times, well, we had velocity squared over our radius squared. So now we actually can just get rid of this mass and acceleration portion. We can slide this over, and we have now that the centripetal force is equal to the mass times this ratio of the velocity squared over the radius. And that's where these actually have come from and how to derive these equations.